Welcome to the deep dive. Today, we're plunging into what can feel like, well, a pretty technical, behind the scenes world. We're talking about the infrastructure that truly powers artificial intelligence. Think of it like pulling back the curtain to see how AI actually goes from just a model on a laptop to a real, functioning system inside a data center. Now, what's really interesting about our source material for this deep dive is where it comes from. It's maybe a bit unexpected. It's from practice questions and the explanations for the NVIDIA Certified Professional AI Operations exam, the NCP-AIO. So our mission today, to pull out the most important nuggets of knowledge from these questions, we want to make these complex ideas clear and, show the practical challenges and solutions in managing AI workloads, especially when you're dealing with powerful NVIDIA GPUs and Kubernetes. And even if you're not thinking about taking the exam, honestly, these insights are crucial for understanding how AI gets real. Okay, let's unpack this.
Absolutely. And, when you look at the NCP-AIO exam's focus areas, they really aren't just academic boxes to tick. They represent the critical pillars, the day-to-day stuff, faced by anyone building or maintaining these AI systems in the real world. We're talking administration, that's a big chunk, like 36%. Then installation and deployment at 26%, troubleshooting and optimization, 20%, and workload management at 16%. So our discussion today is really going to shine a light on the specific tools and the best practices that tackle these exact operational areas.
Okay, let's start right at the beginning then, laying the groundwork. So you've got these amazing NVIDIA GPUs, raw power just sitting there, but getting them to work smoothly in something complex like Kubernetes, well, it's not just plug and play, is it?
Not at all.
What's the first really critical piece, the thing that acts as the bridge, making sure those GPUs are, fully operational and ready for AI across the whole cluster?
Right. And what's fascinating here is just how much complexity this one tool abstracts away. We're talking about the NVIDIA GPU Operator. Its main job in Kubernetes is basically automating the deployment and the management of all the necessary bits. Things like GPU drivers, the device plugins Kubernetes needs, monitoring tools, and to make sure the GPUs are properly set up and, just as importantly, monitored consistently across the whole cluster. It really takes away a massive headache, integrating that powerful hardware into a dynamic software setup. Makes it scalable, repeatable.
Okay, so the GPU operator gets the hardware talking to Kubernetes, but then how does Kubernetes actually handle the AI tasks themselves, those pods running on the worker nodes? What's the component that's like the local manager for those pods, making sure they run correctly right there on the node?
That would be Kubelet. That's the essential Kubernetes agent running on every single worker node. It's responsible for managing the pods assigned to that node, making sure the containers inside are running, healthy, doing what they're supposed to.
So it's kind of the node's supervisor.
Yeah. Exactly. It's crucial for orchestrating the workloads at the execution level. If the main Kubernetes control plane says, run this AI job here, Kubelet is the one that actually pulls the container image, talks to the container runtime, allocates resources like GPUs to that pod, and keeps an eye on it. And critically, something goes wrong with the pod, Kubelet tries to restart it or flags the problem. That reliability is key.
Got it. Okay, let's shift gears slightly. Imagine setting up a new Kubernetes cluster specifically for AI. Maybe you're using something like NVIDIA's Base Command Manager, BCM. Could you maybe quickly explain what BCM is first?
Sure. Think of Base Command Manager, BCM, as a kind of management layer, a platform really, designed to simplify deploying and managing AI infrastructure. It bundles tools to help you quickly set up, monitor, and maintain your Kubernetes clusters, especially on NVIDIA hardware. It handles a lot of the tricky integration bits, GPUs, networking, storage specifically for AI.
Right, simplifying the setup. And within that setup, when you're thinking about AI workloads, what kind of storage is just absolutely non-negotiable? What do you have to have?
Well, yeah, that's critical. AI workloads are incredibly data hungry. They need really high throughput and parallel data access. So what's non-negotiable is having a high-performance parallel file system available. Things like Lustre or IBM Spectrum Scale. Verifying this before you deploy is absolutely crucial.
Why is that so important, the parallel aspect?
Well, if we connect this to the bigger picture, think of your AI workload, especially training, as a super fast race car. Your GPUs are the engine. If your storage is like a narrow, bumpy country road, it doesn't matter how powerful the engine is, right? You'll be stuck waiting for fuel, or in this case, data. A parallel file system is like building a multi-lane highway directly to the engine. It allows many data streams simultaneously, ensuring your GPUs aren't starved for data.
Yeah.
They can run flat out, It prevents those I/O bottlenecks.
That's a great analogy. Makes sense. Okay, practical challenge time. You need to get containers from NGC NVIDIA GPU Cloud into an offline, air-gapped data center, no direct internet. How do you actually transfer those container images? They can be pretty big.
Right, that's a common scenario in secure environments.
hmm
The command you'd use here is Docker Safe. It lets you export a Docker image, all its layers and metadata, into a single tar file.
Like packaging it up.
Exactly. You package it up. Then you can take that file and, yeah, for AI models, it could be gigabytes and transfer it to the offline system, maybe over a secure network link, maybe even physically on a drive. Once it's on the offline system, you use Docker load to import it back into the local Docker registry. This way, you can run your containerized AI workloads without needing any external network connection. It's essential for those isolated environments.
Okay, that covers getting things set up and deployed. Let's move into optimizing performance and managing the workloads once they're running. GPUs are expensive, right? In a shared cluster, maybe multiple teams running jobs, you want to make sure you're getting the most out of them. How do platforms like Run.ai help with that? Sharing those resources efficiently.
Yeah, Run.ai tackles this head-on. Its key function is really about dynamically allocating fractional GPUs. So traditionally, if your job needed any GPU, it might lock up a whole, very expensive card, even if it only needed, say, 20% of its compute power or memory.
Which seems wasteful.
Totally wasteful. Run.ai allows the system to intelligently slice up the GPU resources and assign those fractions to different jobs running concurrently. This means you can run many more experiments or training tasks on the same physical hardware. It massively boosts utilization and, well, the return on investment for those GPUs. It moves you from static allocation to a much more fluid, efficient pool of resources.
That sounds incredibly useful. And building on that idea of smart allocation, once you have nodes with GPUs, how do you make sure Kubernetes actually sends the jobs to the right nodes? You don't want jobs needing GPUs landing on nodes without them or piling up on one node while others are free, right? What Kubernetes feature helps control that placement?
That's where node affinity comes in. It's a standard but powerful Kubernetes scheduler feature. It lets you define rules or preferences about which nodes a pod should run on. So you can say, this pod must run on a node with label GPO ENILA 100, or this pod prefers nodes with high memory.
Ah, so you guide the scheduler.
Precisely, you guide it. This helps ensure that your GPU-hungry pods actually land on nodes that have available GPUs, balancing the load and making sure resources match the requirements. This raises an important question about how you intelligently allocate these scarce resources across the whole cluster. Node affinity is a key tool for that.
Makes sense. Okay, let's switch to troubleshooting. Things inevitably go wrong sometimes. Picture this. A data scientist reports their training job starts fine, but after like 30 minutes, the speed just tanks, drops significantly. You check the basics, storage bandwidth looks fine, it's stable. But you notice the CPU usage on the node is spiking really high. What's your first thought? What's the next logical step?
Okay, stable storage, but spiking CPU causing a slowdown. The most logical next step, based on that evidence, is to check for rogue or unexpected background processes consuming CPU resources on that node. It's a classic situation. Something else is running on that machine, maybe some system task, maybe another user's stray process, and it's stealing CPU cycles away from the main AI training application.
So look beyond the AI job itself.
Exactly. You have to look at the whole node context. It's easy to get tunnel vision on the AI application, but sometimes the culprit is hiding in plain sight, just chewing up CPU.
Right. Now, staying with monitoring, but scaling it up. Imagine a big cluster, maybe managed by Slurm, which for listeners is common in high-performance computing. You need to keep an eye on the health of hundreds, maybe thousands of GPUs across all these nodes, specifically things like memory usage and temperature. Is there a tool designed for that kind of large-scale monitoring?
Yes, definitely. For that scenario, the tool you typically reach for is DCGMI. That's the Data Center GPU Manager command line interface. It's specifically built by NVIDIA to efficiently query health metrics, memory usage, temperature, power draw, utilization across many GPUs on multiple nodes. It's designed for exactly these kinds of large HPC or Slurm-managed clusters where you need a consolidated view to spot problems quickly, like GPUs overheating or running out of memory before they cause job failures.
DCGII, got it. Okay, let's get even more specific, down to the hardware interconnects. Say your Fabric Manager service, which manages those high-speed NVLink or NVSwitch connections between GPUs, reports a link training failure. This sounds serious, like the GPUs can't talk to each other properly through that fast interconnect. What's the very first thing you do to troubleshoot that?
Yeah, a link training failure means that fast connection isn't coming up correctly. The logical first troubleshooting step is usually to restart the Fabric Manager service itself. And then, immediately after restarting, you need to examine its logs very carefully. Often it might be a transient glitch that a restart clears.
Huh.
But the logs are key. They should provide specific error messages or clues about why the link failed to train. Is it a configuration issue? A problem with a specific GPU or cable? The logs are your starting point for diagnosing that low-level communication problem.
Always check the logs. Okay, final scenario. You have a containerized AI workload running in Kubernetes. It's clearly having storage performance problems. The logs show these frustrating intermittent delays, specifically during data loading phases. Not always slow, but pausing inconsistently. What's the most likely cause behind that kind of symptom?
Intermittent delays during data loading. When you've pinpointed storage as the area, that almost always points to low throughput on the storage backend.
Throughput, not latency necessarily.
It could be related to latency, but the intermittent nature, the pauses during bulk loading, strongly suggest the storage system just can't sustain the rate of data flow the AI job is demanding. So what does this all mean? It means the storage can't keep up. The job starts loading data, maybe it goes fast for a bit, then the storage hits its limit and things grind to a halt until it catches up. Then the cycle repeats. It's that classic bottleneck. The GPUs or CPUs are sitting idle, waiting for data because the storage pipe isn't wide enough or fast enough to keep them fed continuously.
That really highlights how interconnected everything is. The GPUs, the network, the storage.
Absolutely. Performance is often limited by the weakest link. And perhaps a final thought to leave you with. AI models are getting bigger, more complex, more demanding all the time. The hardware keeps evolving too. This means the tools and techniques for managing the infrastructure also have to constantly evolve. Continuous learning isn't just recommended, it's essential in this field. So maybe think about this. What new management and optimization challenges do you foresee emerging as AI models become even more demanding in the future? It's definitely something worth pondering.